So we can represent ionic bonding using a Lewis dot structure by actually showing the transfer of electrons. What you see is you see the Lewis dot structure for sodium. Sodium has a single electron, and we know that because it's in group 1. And chlorine has 7 valence electrons, and we know that because chlorine is in the halogens or group 17. So you can see that here. You see sodium right here in group 1, and you see chlorine right here in group 17. So, because we know that, we can go back and we can say these are the Lewis dot structures. Now, for a ionic bond, the electron actually leaves and goes to the chlorine. As a result, sodium has a +1 charge. Now, we're not actually going to draw the shell that opens up as a result, because remember, there should be still 8 electrons in this next shell. We're not going to draw that. If you take the 1 valence electron away, there are now 0 valence electrons remaining here. You transfer that electron to the chlorine, and now you have chlorine with 2, 4, 6, 8 electrons, so chlorine is happy. And sodium is happy because it also has a closed valence shell. In other words, it has 0 valence electrons, just like chlorine does at this point. Covalent bonds. So you can draw covalent bonds using these Lewis dot structures as well. So once again, we start off with diatomic fluorine, and we say you've got 2 electrons right there that are shared, and you draw them together just like you see here. But really that gets to be kind of confusing for people. They say, okay, these dots, what do they actually belong to? So instead we represent shared electrons by a line right here, which we call the covalent bond. So the covalent bond takes the place of the shared electrons, and it represents 2 electrons that are between them. Now, the problem is that there are certain situations in which you need more than 1 electron in order to satisfy the octet rule. And one of those is when you have the molecule C2H2. So, if you were to draw it, you have carbon, which has 1, 2, 3, 4, carbon, which has 1, 2, 3, 4, and hydrogen, which has 1, and hydrogen, which has 1. Well, it's pretty easy to bond up the carbons and the hydrogens, and you say those are represented by a line. The problem becomes when you look at the rest of them. This carbon has 3 remaining electrons, and it thinks it has 5. It thinks it has these 2, and it thinks it has these 3, so it's 3 electrons short. This carbon is in the same boat. It thinks it has these 2, and it thinks it has these 3, so as a result, it thinks it has 5 electrons. By each carbon atom sharing all 3 of its electrons, okay, each carbon now thinks that it has 8 electrons. If you look on the actual dot structure here, this carbon thinks it has these 8 electrons. Okay, this carbon thinks it has these 8 electrons. So as a result, both carbons are happy because they think of themselves as being satisfied by the octet rule. This hydrogen thinks it's happy because remember, hydrogen is an exception to the octet rule. This hydrogen thinks it's happy because it is an exception to the octet rule. Now, whenever you have multiple bonds, you draw multiple lines. You draw one line for each pair of electrons. So in this case, we have 3 bonds, or it's called a triple bond. Okay, the triple bond, or any sort of multiple bond, a double bond, a triple bond, the usual suspects tend to be carbon, nitrogen, and oxygen. Those tend to be the things that form more than one bond, either a double or a triple bond. Now, just coincidentally, these are the main components, not so coincidentally, these are the main components of life, carbon, nitrogen, and oxygen, because of their versatility. So, you have this right here. If you were trying to figure out how to do the connectivity of carbon dioxide, remember carbon dioxide is CO2. The first thing you do is you pick a central atom. Now you tend to pick a central atom based on what there's only one of. That's kind of the easiest way to do it, but it is more of an art than any sort of hard and fast rules. So the first thing that you do is you pick a central atom. I pick carbon, and then I put oxygens on either side. Then what I need to do is I need to count the total number of valence electrons available. And how I can know that is I look once again at the Lewis dot structures or the periodic table. If you were to look at the periodic table, remember carbon's in 14, Okay, so you have carbon right here in group 14, and that means it has 4 valence electrons. Oxygen's in group 16, which means it has 6 valence electrons. So as a result, you get these things right here. Oxygen, oxygen, carbon, and you have 16 total electrons. Okay, so we have 16 electrons to make each one of these elements satisfy the octet rule. So the first thing we want to do is we want to bond all of the elements. They're all connected to each other somehow. So what I do is I draw a bond connecting carbon and oxygen, and remember those represent 2 electrons each. So as a result, I subtract 4 electrons from the total, and I have 12 electrons remaining to try and satisfy the octet rule. Now what I need to do is I need to count how many electrons are required to satisfy the octet rule. Okay, this first oxygen thinks it has 2 electrons and it needs 6 more. This oxygen thinks it has 6 electrons and it needs 6 more. And this one, this is a mistake, this carbon right here thinks it has 4 electrons, and so it would need 4 more electrons. So, as a result, there's a total of 16 electrons that are required. If you've got a problem, if you've got 16 electrons that you need, and you only have 12 electrons that are actually there. So what we do is we then go ahead and we say, all right, if I need 16 electrons and I only have 12, what I want to do is I want to add a double bond. So I add a second bond between this carbon and this oxygen. I have no idea if that's the one that actually occurs. I just kind of take a look at it. There's no way of knowing which one is which. So now what I do is I subtract 2 electrons from my total. Okay, I had 12 electrons available. I used 2 of them. I now have 10 electrons available. Okay, I look at it again and I say, okay, this oxygen still needs 4. This oxygen still needs 6. And this carbon still needs 2. So if you look, I now have 12 electrons. Okay, those 12 electrons are needed. I only have 10, so that doesn't work. So what I need to do is I need to add another double bond. Okay, change colors just to represent the next one. So I add another double bond. Okay, when I add that second double bond, we'll go ahead and erase these. When I add that second double bond, what you get is this oxygen now thinks that it needs 4 electrons. This oxygen now thinks that it needs 4 electrons. This carbon is good. It thinks that it has 8 electrons already. Now, we added another double bond, so we have to subtract 2 more electrons. And so I have 8 electrons available, and I need 8 electrons. So this is something that requires practice more than anything else when trying to find double bonds. So this is what we talked about. We saw that we had an electron deficit. We repeated our process. And then finally we say, okay, we have 8 electrons. We needed 8 electrons, so we can go ahead and fill them in and say, okay, this right here is the structure of carbon dioxide. It's a carbon with 2 double bonds, each 2 double bonds, 1 double bond to oxygen and 1 double bond to oxygen. You have an example here. It says the compound CH2 cannot be formed by stable covalent bonds. Explain why not and justify your answer using the clear method. So the first thing we want to do is we want to look at the Lewis dot structures. So we say C, and then we have hydrogen, which has 1, and hydrogen, which has 1. So the first thing you need to say is, okay, I'm going to draw my bonds. So I'm going to have hydrogen, carbon, hydrogen. Okay, I had 1, 2, 3, 4, 5, 6 electrons available. Okay, I have 6 electrons available, and I used 4 of them. Okay, so I have 2 electrons left that I can use. So now let's look at the stability of each. This one right here, this hydrogen is good. It thinks it has 2 electrons. This hydrogen is good. It thinks it has 2 electrons. But when I look at the carbon thinks that it has 4 electrons. Now carbon wants 8 electrons. And as a result, it needs more electrons. But I only have 2 electrons to give it. Okay, if I give it 2 electrons, I'm going to be too short. And so people say, okay, at this point, you'd do a double bond. You'd say, okay, well, I put a double bond here. Well, if I put a double bond here, number one, that's not going to work. And the reason why it's not going to work is because hydrogen cannot have 4 electrons. That can't work. Okay? This other hydrogen cannot have 4 electrons, so that's not going to work. But in addition to that, even if that hydrogen could take on 4 electrons, it would still only give me 6 electrons on this carbon, so I'd be short. So there's no way of being able to make this work. Now, if it was something different other than hydrogen, like we saw earlier with oxygen, okay, it would work because it could form a double bond. But hydrogen can't form double bonds because it only wants 2 electrons. So hydrogen and helium are incapable of forming double bonds with any sort of compound. Draw the Lewis dot structure for perchlorate. First thing you have to be able to do is memorize our polyatomic ion that we have, which is perchlorate, which is ClO4, and it has a negative charge, and that negative charge is going to come into play. So the first thing I need to do is I need to pick a central atom, and I pick the single one. So chlorine becomes my central atom. I have one bond, one bond, one bond, and one bond. Now, as far as the electrons that I have initially available to me, chlorine has 7 valence electrons because it's a halogen. It's in that last, or it's in group 17. Oxygen has 6 electrons each because they're in group 16, and there are 4 of them. So as a result of that, you have 7 plus 24, or 31 available electrons. Now, this negative charge means that you actually have an extra electron. So you have 32 electrons that are actually available. Now, as drawn, by connecting all of these things together, you can see that chlorine is already satisfied. Okay, chlorine has 8 electrons around it, 2 from each bond, so it's good to go. So now we need to look at the Lewis dot structure for oxygens. I have 32 electrons available. Okay, I've used 8 for bonds, so I got to subtract those, and I get 24 electrons that are remaining. Okay, each oxygen needs 1, 2, 3, 4, 5, 6 electrons to be able to satisfy the octet rule and say that it has 8 electrons. So if I take 24 and I divide it by 4, what you end up with is that is 6 electrons. So I can distribute 6 electrons to each atom, and in fact that will work, and it will allow each atom to satisfy the octet rule. So there are no double bonds in perchlorate. Instead, what you're left with is something that looks on the order of this. Chlorine in the middle, single bonds to surrounding oxygens. That's why this becomes really important. Okay, if you had an odd number of electrons, you wouldn't be able to form bonds. You'd have a leftover electron, and it gets pretty messy from there. Sulfur hexafluoride is an example of an exception to the octet rule. Remember we said it's a general guideline, it's not an actual rule. It says for this molecule to be stable, it has 12 electrons. Draw a Lewis dot structure for this particular compound. Okay, so what we're going to do is we're going to kind of come down here, and it was sulfur hexafluoride. Okay, sulfur hexafluoride is SF6. So we take sulfur, which is in the middle, and sulfur has 1, 2, 3, 4, 5, 6 valence electrons. Okay, the first thing I want to be able to do is I want to be able to bond them to the fluorines. So I'm going to go ahead and take each one of these. I'm going to erase the the valence structure, and I'm going to go ahead and draw the bonds. I'm going to say 1, 2, 3, 4, 5, 6, and I'm going to put F's there. Okay, sulfur had 6 electrons. Fluorine brings 7 electrons, and there are 6 of them. So I have 42 electrons from fluorine plus the 6 from sulfur, or 48 total electrons. Now, by making the bonds with the fluorine, I've used up 2, 4, 6, 8, 10, 12 electrons. So I've used 12 electrons, and that leaves me with 36 electrons left. Each fluorine needs 6 more electrons. You need to be able to say 1, 2, 3, 4, 5, 6 to make fluorine satisfied. So if you divide each one by 6, you're given that there are 6 combinations that you can do, and there are 6 fluorines. So I'm good by just filling in the rest of the electrons, which can be kind of tedious for sulfur hexafluoride. The larger the molecules, the more tedious the Lewis dot structures can be.